Bismillahirrahmanirrahim. Assalamualaikum dear students. I am Mr. Kadim Khan and I am a lecturer in the Institute of Computing, Guwahati University of Science and Technology. Today we will take lecture number 25 of the subject of software engineering, in which we will discuss software testing. In the software testings, we will discuss the equivalence class partitioning, boundary value analysis and the control flow graph. CFG is very much important because it is the core of software testing and it gives us the exact number of test cases to be developed in for testing. So that's why this topic is very much important. This is the discussion agenda. It contains the topics of functional testing versus structural testing, black box testing, then we have the equivalence class partitioning, boundary value analysis and the white box testing. In white box testing, we will discuss the testing of statement coverage, branch coverage and path coverage. Then we have very important topic of the control flow graph and we have also examples of the CFG. We will also continue the CFG or control flow graph in the next lecture as well. So that's why this is very much important in terms of software testing. Okay, functional testing versus structured testing. As dear students, the name indicates the functional testing means the testing which tests the functionality of the system. So when the runtime we perform input-output and then the system processes this input and produces some useful information of the output, and then we test that whether this output is according to the SRS or not. Then it is called the functional testing. So basically functional testing is also called black box testing. Black box testing because the structure or the code of program is not tested here directly. We can test the executable files or runtime of the product. So test cases are designed using only the functional specification of the software, that is without any knowledge of the internal structure of the system. For this reason, black box testing is known as functional testing. So the black box testing is also called functional testing because we are not concerned with the system structure of the programming. We only test the software product, the runtime product of the system. Okay. On the other hand, the white box, which is against the opposite of the black box testing. In the white box testing, we test the code or the structure of the software or the internal structure of the software. Therefore, the white box testing is also called the structure testing. We will test that the structure is working properly or the program statements are executing properly. Then it is called the structure test. This is the difference between functional test and the structure test. Now, again we will discuss the black box test in very much detail. Black box testing are designed from the examination of the input-output values only and no knowledge of design or code is required. Basically, black box testing is a test which is done based on the input-output. So here we don't concern about the system programming. So we don't test the internal structure of the system. The following are two main approaches to design the black box testing. So when we design the black box testing, we use two different techniques. These techniques specifies that how the test cases will be designed. Here are two different techniques. One is called equivalence class partitioning and the second one is called boundary value analysis. Now equivalence class partitioning. As its name indicates, we partition the input into multiple equivalent classes here. So in this approach, the domain of input values to a program is partitioned into a set of equivalent classes. The main idea behind defining the equivalent class is that testing the code with any one values belonging to an equivalent class is as good as testing the software with any other values belonging to that class. So basically, when we design the equivalent class partitioning of the softwares, then we also design the test cases based on that partition. So when a certain values from that equivalence class partition is taken as the input for a test, then it is equivalent that the software will perform very well against any other input. Okay, equivalence classes for software is designed by examining the input and output data. Based on some input and output data, we design the equivalence class partitioning. Right. Equivalent class partitionings have the following classes. Basically, first of all, we will take the input data values to the system, and we will in fact specify the range of the values. For example, if a person who want to take admission in a university, his or her range should be more than 18 years and up to 60 years, for example, up to 18 or 60. If a student enter his or her age less than 18, for example, 2 years or 3 years, so he is not eligible to apply for the university because he is a school student. So then we in fact specify the range here. So one valid and two invalid equivalence classes should be identified. Here we define one valid and two invalid classes. Here is the example of the equivalence class partitioning. For example, a software that computes square roots of integer data. So that can assume the values in the range of 0 to 5000. There are three equivalence classes for this. For example, we want to compute the square root of the integer data. So the integer data must be between 0 to 5000. So there we can, for example, define three different equivalence class partition. So the set of negative integer, the set of integer in the range of 0 and 5000, and the next integer larger than 5000. So for example, we can put different inputs here to the system. First of all, we will provide the values which is less than this range. That may be the negative values. For example, -1, -5, -3, etc. And secondly, the set of integer between this range, 0 to 5000, this range. This may be, for example, 500 or 600 or 1000 or 2000, 4999 may also be the one of the value. And the third one, the larger number, 5000. So this may be, for example, 5500 or 5001, 5010, 5006. So the value which will be in the range will give us certain value. For example, it will be processed correctly, but the value which is less than this range and the value which is greater than this range, the system must have give us some false flag so that the system is unable to process the data. So therefore, the test cases must include a representative of each of three equivalence classes and possible test. This will be one of the possible tests in the which is an example of equivalence class partitioning. -500 which is between this range, -5 which is less than this range, 500 is between this range which is one of the value in this range, 6000 is above the 5000. So for example, this value -500 and 6000 will in fact the system will raise certain message that this is out of range, but 500 is within the range. So this is the good example of the equivalence class partitioning. The second method is called boundary value analysis, which is one step up than the equivalence class partitioning. In the boundary value analysis, we define the special boundaries of the values as well, with the one less than and one greater than values, as like the equivalence class partitioning. So because here we define more exhaustive testing, so that's why boundary value analysis is better. Okay. So boundary values analysis leads to selection of two test cases, the boundaries of the different equivalence class partitioning. Let us take the same example that we want to compute the square roots of integer in the range of 0 to 5000. Right, equivalence class partition test was, for example, -5, 500, 6000. So there were only three values in the equivalence class partitioning. But the boundary analysis says that it should actually be the boundary values. For example, 0 or 5000 is the boundary values, one value is less than the boundaries and another one values which may be the greater than the boundary. So for example, -1 which is less than 0. It cannot be, for example, -5, -6, etc. And 5001 which should be greater than 5000, it should be 5001. So if the values between these two values, the system will compute some output, but these two values, the system will raise exception, that it is out of range. Now, white box testing. White box testing is that test which is also called structure testing. In this test, we test the structure of the system. So it is also required to test the system structure. For example, in the black box test, if the system identifies certain defects, then the white box testing will be very much useful, and we also conduct the white box test to identify the defects of the black box testing. For example, maybe this may be the certain expression errors, that may be the logical errors, or it may be certain errors of the looping or structure of the code, incorrect calling of the function. So that is the white box test. Now, for example, we have the test of error detected by testing strategy B and types of error detected by testing strategy A. So we can say that A is a stronger testing strategy than B. A and B are two strategies, but A is stronger than B, while A includes B as well. B also includes some part of the A, but A includes fully B, but B includes some part of the A. So that's why A is stronger strategy than B. Now here, this is another strategy, for example, testing strategy A. This is another testing strategy B. But A and B are complementary testing strategy. Complementary means that this area is common between these two sets. So that's why this is called a complementary testing strategy. So these two are not good testing strategies because this shares only one point, one common area, but this is more powerful. A is more powerful, which is the exhaustive testing, also called complete testing. Okay, white box testing. There are three different types of white box testing. Again, I mentioned that white box testing is that testing which tests the structure of the system. It tests the programming structure or particular module in terms of the coding. So three techniques we have to discuss with the white box testing. First one is called statement coverage, second one branch coverage, and third is the path coverage. Okay, statement coverage. Statement coverage is that strategy we design to test cases that every statement in a program must be executed at least once. For example, if there is a statement which is not executing even if we provide any test data to the system, then that particular statement should be removed from the system. So statement coverage is that testing in which every statement of the program must be tested through a particular test case. So the principal idea governing the statement coverage strategy is that when a statement is executed, it is very hard to determine if an error exists in that statement. But yeah, that is also a very hard strategy because we can't make sure that how to test that particular program, that every statement of the program must be executed. So that's why it is very much difficult testing strategy. Also, you must have to design certain test case which can test every statement of the program. So the disadvantage of this strategy is that however, executing some statement once and observing that it behaves properly for that input, there is no guarantee that it will behave correctly for all input values. So it is very clear that for one value, the particular statement will be executed. If we provide another input value, another types of statement will be executed, and so on. Exactly like in the switch cases, that if we provide one types of data, it will execute only one case statement, and if we provide another sort of data, it will execute another switch statement or case statement, and so on. So that's why it doesn't guarantee that every statement should be executed for one data. Now, statement coverage examples we are doing here. This is the GCD, equivalence algorithm code, greatest common divisor. It computes the greatest commons between two values. For example, x. This is the function which returns integer values. So it takes two parameters x and y. For example, x, y should be integer here, which are defined here. So, for example, the greatest common divisor of the 30 and 50 is 10. This is called greatest common divisor. So here it is the int x, y, number 1, while x is not equal to y. If x is greater than 1, then x is equal to x minus y, else y is equal to y minus x, and return x. So this in fact tests that if two values are greater, then it is tested here. So this is the Euclidean algorithm which computes the GCD of two values. Okay. By choosing the set x4, y3 and x3, y4, we can exercise the program that all all statements are executed at least once. For example, if we provide two test cases 4, 3 and 3, 4, in one first case 4 is greater than second, and in second case first value is less than 4. So if this value test here that while x is not equal to y, so in both cases this is true, loop will be executed. So first one is greater than the second, then this part will be executed, and in the second first one is less than the second one, for example, so else part will be executed and in return x will be computed. Okay. Now branch coverage. Branch coverage is that testing case in which every branch of the program is tested, so that the branch must be executed for the true and false values. Okay. So this is against that the branch testing guarantees statement coverage, and this is a stronger testing strategy compared to the statement coverage based. The branch coverage is a test that is executed for testing the branches. Branches includes the loop statements and the if else and switch statement. So branch coverage provides us better idea as compared to the statement coverage. So the Euclidean algorithm, branch coverage algorithm, we can provide this test data and it will cover every statement. For example, x3, y3, this is the equality, and x3, y2, this is first one is greater than the second one, and 4, 3 first one is also greater than second, and 3, 4 first one is less than the 4. So this is more exhaustive testing strategy. So this is a good testing case because it tests all the algorithm. For example, I want to go back. For example, 3 is less than 5. So here one will be tested for true. 3 is not equal to 5. For example, 5 is less than 3. So then while loop will be also executed. But for what test cases the while loop will not be executed and it will be interrupted. For example, 3 is equal to 3, in which this condition becomes false. So automatically this system will return x3. The GCD of 3 and 3 is 10, 3. 3 and 3 is 3. So return x first number will be returned. So and then if x is greater than y, we should provide set test case in which x is greater than y. So also we should provide set test case in which x is less than y. So if and else module will be executed. So this branch coverage tested the test software for every statement. So that's why branch coverage is much powerful strategy than the statement coverage. Next one is called the path coverage. Path coverage, in fact, it is exactly like the branch coverage, but this uses a different techniques. The technique is called control flow graph. The path coverage based is a testing strategy that is used to design the test cases such that all the linearly independent paths in the program are executed at least once. A linearly independent path can be defined in terms of the control flow graph CFG of the program. CFG is exactly like flow charts, and in which there are multiple statements in the CFG. So for example, you have input-output statement, processing statement, and conditional statements in the CFG. So in other words, control flow graph describes how the control flow to the program has been executed. In order to draw the control flow graph of the program, all the statement of the program must be numbered first. We first number the statement. This is the example of the CFG or control flow graph. If the statements are in the sequence, for example, there are two formulas or expressions. A is equal to 5, B is equal to A steric B 2 minus 1, A steric 2 minus 1. So we can sequentially draw the CFG of these two statements, 1 and 2. Then we have the selection statement. If A is greater than B, C is equal to 3, else C is equal to 5, and at the end C is equal to C multiplied by C is also executed. So we will just number here 1. If 1 is true, then go to 2, otherwise go to 3. If 1 is true, go to 2, otherwise go to 3. And at the end, 4 statement is executed. Here this 4 statement is executed. So 4 must be executed in any case. And we have the iteration while A is greater than B, B is equal to B minus 1 and B is equal to B starting A, iteration close, that means loop close, and at the end C is equal to A plus B must be executed if even the loop is false from the beginning. So first 1, then 2, then 3, and this loop is executed. If for example loop is in first from the beginning, so then we will come to the for statement. If loop is true, and then the loop will be continued. So while loop is in fact tested here. So for example, if this statement is false from the beginning, from 1 the system will must test 1 and then will come to the 4. And if it is true, then it will take statement 2 and statement 3 and this loop will be continued. So this is the simple three different example of the CFG. Now let us take very complex examples here. For example, int compute GCD int x comma int y when x is not equal to y, if x is greater than y, x is equal to x minus y, else y is equal to x minus y minus x, return x. Okay, the CFG of this program looks like this. Okay, students, you have to note that, you should note that, for example, this is a function, and the body of the function starts from this parenthesis or the brackets. Okay. And the function of this, the body of this function is ending here. So that's why it's not necessary to number the beginning of the function and the end of the function. Because the control flow graph, basically it tests the control, so that's why we have to number from the controls and from the statements. For example, here is the while loop. So while loop, while if in the while loop there is the if statement. So if it is true, then x is equal to x minus y, else y is equal to x minus y, and at the end 5 will be is the combination of the connecting point of the 3 and 4. And again it will go up to test the loop. If the loop is true, then again 2, 3, 4, either 3, 4 and then 5. And again if the loop is true, then it will come down in this fashion. So immediately if the loop becomes false, then automatically the system will come to the return statement, which is the return statement, return x. So then the GCD will be computed, and x will be the GCD of the two values. So this is the example. In the next lecture we will do some more complex examples. Here I have written another example for your practice purpose, that draw the GCD of the following code using the CFG, show the complexity of the code. So the complexity of the code we will discuss in the next lecture, but you should draw the GCD of this code. This is the ending bracket. You can see 3 starting brackets, 1, 2, 3 and 1, 2, 3, 3 ending brackets. So this is for your practice purpose. It is different than this program by little bit, but it is also very much interesting. So I will give you little bit clue. You should start numbering from here, 1, 2, 3, 4, 5. If you are numbering this, then you should also number the last brackets. If you are not numbering the definition of the function, you should also leave the closing brackets. So that's why you should start numbering from for loop, 1, 2, 3, 4, 5, and then you will design the CFG of this example from taking help from this example of the GCD. Okay. Now student, this is the lecture, end of the lecture. If you have any question, you can drop an email to me, that is m.kadim@kust.edu.tk, and if you want to read more about this lecture, so you can use the references here. So I will answer you immediately if you send me an email for your quiz. Also you can send your quiz through TCMS as well. Thank you very much.